2.3, we're looking at functions and mathematical models. So we're just looking at different types of functions that we can classify. We're not doing a whole lot of modeling in this course, but depending on what you're looking at, you may have to chart the data and try and find mathematical models that actually fit your data. It's never clean. You're always going to have outliers, but the more data points you have, the more you can model. I'm just going to focus on the different types of functions that we're going to look at, and we're going to be taking derivatives of these very soon. So it's important to understand what type you have, and then you'll know what you need to do when we get into derivatives. So first, we're just looking at polynomials. We've talked about it. It's come up a couple of times already. So here's the basic form for the polynomial. We have an x to the n plus an minus 1 x to the n minus 1. So all those an's in the beginning just tells me the coefficient of what degree term. So this an is because it's with the nth degree term. N minus 1 is because it's with the n minus 1 degree term, and so on. The constant is a naught because there's no variable. We could put one in and make that x to the 0 power because that's just equal to 1. But that's why the last term is a naught. The very first, the highest degree term, of course, can't be 0 or else that term wouldn't be there. All these coefficients are real numbers. And all of the exponents, if it's a polynomial, they have to be whole numbers. So here's an example. I have a polynomial, 5x to the 4th minus 3x squared plus 2x plus 5. If this was like x to the negative 4, it wouldn't be a polynomial because they have to be whole numbers. So the degree of this is the highest degree term, which is the 4th power. So it's a 4th degree polynomial. And I just wrote out the coefficients for you. The x to the 4th had a coefficient of 5. There was no x cubed term here, so that coefficient is 0. The x squared had negative 3. The x to the 1st had 2. And that constant, the a naught term, is a 5. We're going to look at linear. It comes up again and again. And so we have y equals f of x, and this is the same notation as above with the polynomials, a1 of x plus a naught. So first degree, we're not used to seeing it written this way, but a linear function is just a polynomial. Here's an example, y equals 2x plus 4. We're used to this slope-intercept form, right? Where m is the slope and b is where it crosses the y-axis. So y equals 2x plus 4 crossed the y-axis at 4, and it had a slope of 2. Here I have a quadratic. So this polynomial, a2x squared plus a1x plus a naught. And again, those coefficients tell me how the parabola, first of all, the a2 tells me how it's going to face. And then it can, depending on what they are, it shifts it to the left or right, up or down. Main thing we want to look at is the a2 for facing up or down, and if it's a negative number, then it faces down. If this a2 is a positive number, it faces up. We're going to be looking at rational functions because when we go to do derivatives, we're going to be using the quotient rule that's specific to this. So we talked about these. It's just a polynomial divided by a polynomial. And we know that our denominator can't equal 0 or it's undefined. So I have an example of a rational function. F of x is x squared plus 4 over x minus 2. So polynomial divided by a polynomial. We know the domain x cannot equal 2. So I put the graph on here for you, and you see that's called an asymptote. So I have a vertical asymptote at 2, and that's what the graph looks like for that particular rational. And then the last thing that we're going to look at before we get into the last part of the course, where we're going to look at logarithms a little bit, logarithm and exponential functions, is the power function. So power function, and then at the end we'll look at taking derivatives of exponential and logarithmic functions. So the difference between a power function and a polynomial is now this exponent could be any real number at all. A polynomial, it had to be a whole number, right? The exponent had to be 2, 3, 4, 1, things like that. But if it's a power function, it's any real number. So here's an example, square root of x. We're always going to rewrite them as fractional exponents. So we get x to the 1/2 power. And then I have this power function, 1 over x squared is x to the -2. It's not a polynomial because of that negative exponent. And then 1 over the 5th root of x cubed. So we need the negative to bring it up. The power is always the numerator, the root the denominator, so x to the -3/5 power. So those power functions and polynomials and quotients and products, we're going to be learning our derivative rules so that when we start composing these functions algebraically, we know what it is we have to do in order to find the derivatives.